Okay, so this, today I wanted to do, and as you could see from the previous session, I kind of wanted to do stuff that was a little bit more experimental compared to last year, meaning I wanted to try some new kinds of sessions. So like, you know, the session on muscular and physical problems related to programming, obviously not the kind of thing that you would normally necessarily talk about at a programming conference, but I think really important to talk about, and you know, that was a fabulous session, so I think that was exactly the right thing. The other sort of stuff that I wanted to try were getting some sort of discussion-oriented things into the, you know, sort of the way that the HandmadeCon format works. And so what I wanted to do with this session was there's sort of this, I don't want to say that it's like a thing we do as programmers, but there's a sort of a way that problems get presented when you are talking about them and you know, presenting them to other programmers. It's usually you present them after they've already been solved. So for example, if you went to look at somebody's blog post on something, or somebody does a write-up or a presentation at a conference, typically what happens is they're like, okay, here's the problem as you know, we solved it, here's how we solved it, and sometimes they give you like a little bit of background of like, here's, you know, sort of what did work, what didn't work kind of stuff. But rarely do you actually sort of go back to look at what was the actual process by which the programming happened that got to this solution. And the reason I think this is really important is because not all programmers in their career, depending on where they're at, have had the experience of having to tackle a completely new problem, meaning not just something that's slightly different from what people have done before, but really something that's completely different from anything anyone's done before, and having to go through this process of figuring out what the problem even is and then solving it. And this is one of the most rewarding parts of programming, in my experience, when you do get to have that experience of pushing ahead somewhere where people haven't really explored. And that process is a lot less about sort of the perfecting of something, and a lot more about just the like exploration and figuring out stage and like putting all of the pieces together. So what I want to do with this session is take a look back at something where this happened in history, which is sort of the advent of texture mapping, real-time 3D texture mapping in games. And real-time 3D texture mapping now we sort of take for granted because a graphics processing unit in your computer will do it for you, right? It's kind of like a purpose-built thing that does this. There's tons and tons of infrastructure there for you, and there's really no question that nowadays, you know, unless you're doing something very specific, you're never really going to have an encounter with this part of the code directly. But when games were still running entirely just on a CPU, they were you know, mostly 2D at the time, and they're making the leap to 3D. One of the things that nobody really knew how to do was to actually do texture mapping fast enough in games, or even really what texture mapping in games would mean. Because again, all of this stuff was happening kind of way back in, you know, that this is early 90s kind of stuff, when you didn't have an internet full of information at your fingertips where you could just search for texture mapping or what that is or what all the, you know, tutorials on it. You literally had nothing to go on but maybe your, you know, college's research library or something like this.
Can we ask how many people were at high school or after in the 90s, in 1995? How many? So most people are younger than that. Okay.
Yes. So what I wanted to do here was sort of gather some of the folks who actually did this kind of work and were part of the process of the game industry sort of figuring out how to do this stuff, getting it into commercial games, and, you know, getting the process to the point where it produced like good visual results at speeds that you could run on what, as we're going to kind of go over, were very, very slow machines compared to the kind that we have today. So with that, please welcome Chris Green, Sean Barrett, John Miles, and Chris Hecker, who will sort of walk us through. So Chris, I'll start with you because you actually made some slides for this, which I think—
I made these at 8 a.m. this morning. I'll let you know.
You are the only person who's ever brought slides to it. So why don't you just get us started by giving us sort of a little bit of information about like what was your first encounter with this, or what was the situation like, the period in time when this sort of work sort of first started happening from your perspective?
So actually, the first time I tried to get something like texture map working, I was working at a company that doesn't exist anymore called Sublogic, which was the the flight simulator company, and I did a couple Amiga flight simulators, and we wanted to get a little more exciting stuff on the screen, and we just tried a couple approaches, and so the first thing I did this really bad texture mapper that involved starting a rectangle and recursively subdividing down to the pixel level in the code, and then outputting a 1 or a 0.
Okay.
And I managed to get a smiley face on a billboard
Well,
at a very slow frame rate.
tell us a little bit about what, so a flight simulator at that time, though,
Yeah.
what did it look like before the texture mapping?
So this is, I guess, maybe the second generation of the Subletics / Microsoft Flight Simulator, where we had switched from wireframe to everything actually being solid colored, and we had 16 different colors in the environment, and hundreds of polygons in a scene almost. Sometimes, I mean, I think our plane model, we had an exterior plane you could look at, and I think it was over 100 polygons, and we worked hard to get it to that size. And so largely what you saw, there's no GUROD shading. Largely you saw just a lot of big blank things, and we would put vector graphics on them, literally. There's a lot of lines and markings just so you'd see something, and randomness in color. It didn't look anything like flying over a landscape does. And particularly, just taking off, airports are full signs and stuff like that. So actually we wanted to have signs, so that would be more important. That was completely impractical. We never shipped that. I tried another one. I was trying to get trees or something on the horizon, and I guess I'll go way in the weeds here. This is on the Amiga, which had a hardware line drawer. And the way that hardware line drawer worked is it had a pattern register that was, to do stipples or dashing. And so what I did was I'd set up a line to draw along the horizon, and I would stuff 16 bits of binary texture into the pattern register and output like a line.
Oh,
so basically I was mapping it this way using a line drawing hardware and the pattern register to do it.
So
that was a little more practical, but.
If I understand correctly, so using the hardware line drawing in the Amiga, which is that on the Blitter?
Yeah, I was on the Blitter.
Okay, so the Amiga had a number of custom chips. I remember there was a Blitter component which was used for kind of moving bits around. I guess it could do like a Bressenham line.
Yeah, it could do a Bressenham line, and it had a pattern that it would cycle through every pixel. So you could basically stuff bits into that and have them show up, in a slant on the
wow.
on the
Okay,
screen.
so essentially what you do is just draw a series of lines with the pattern in the pattern register.
And that was actually fast enough, but the problem I had was actually getting the lines to. I probably could make it work now.
Okay.
But there wouldn't be much use to make it work, but I couldn't get the lines to fill the space all the time. I have gaps.
Okay, so this was on the Amiga, and you were looking at this sort of thing, and this is generally the company in general is looking at this and going, we need to figure out ways to get more visual detail, because that's the genesis of why we want to try and do this?
Yes, particularly landscapes and signs.
Now, why did anyone there know what texture mapping was? Because there is research around this and others. Can you give us a little thing about the relationship?
I don't think we ever used the word texture mapping.
Okay.
We didn't really, we didn't really understand it. The way that, I guess a lot of graphics, particularly there were a lot of ways that, maybe in particular there, we did the 3D math and transformations and the precision that actually made texture mapping not, even if you had a texture mapper, it would have been hard to fit into the pipeline because there's a lot of old fixed point tricks, and I guess I could describe it as by the time we have a polygon, we don't actually know its 3D coordinates, and we can't get them back.
Okay.
Because if you're trying to fit everything in 8 or 16 bits of precision, when you do the 3D transform, after you've subtracted the origin, you can multiply or shift the result by any old number you want, and it's still the same point on the screen.
Right.
But it's not invertible back to what it was before.
Okay.
And so our point transform is always doing that. It's always shifting stuff into a certain size. So I couldn't figure out how to clip it or do anything like that because it was kind of impossible.
So basically what you're saying is that when you were doing, because I guess the other point this is sort of the discovery process of like what things were like at this point. Yeah. The floating point math sort of thing is after this point in time, right? Because a stock Amiga has no floating point unit, right?
Yeah, and this software was originally developed for 8-bit computers anyway.
Okay. Right, because it was for Apple II originally.
Apple II, Commodore 64 was the big seller.
And so the Amiga, even though the Amiga is 16-bit at this point.
That was, at least not only do we not, getting the Amiga was amazing because we had a multiply instruction instead of a giant macro that goes on for 4 pages to multiply 2 numbers.
The funny thing is that Bruce Artwick, who ran,
Yeah.
he was so far ahead. Like, you guys were using quaternions before anyone even knew what they were.
We did use those, but we wrote.
But
he
it was
wrote
in his
about-
book. Yeah, he wrote about
in his book, yeah.
I mean, it was way ahead.
He knew about quaternions.
Yeah,
at that
Bruce
point.
Artwick's Flight Simulator book from.
Yeah, if you ever look,
80
there's a
whatever.
classic. A lot of programmers, old school, would all have it.
Yeah.
He wrote a book, it's kind of
What was it
in
called?
a Foley Van Damme era.
Is it microcomputer
range.
graphics displays, something like this?
Something
It's
like that.
Yeah, and it was about his.
They had a
It talked
quads
about
chapter.
programming on the Apple and programming on commercial flight simulators that he'd worked on, and kind of have a lot of esoteric things. At the time, we used to joke about the quaternion chapter on there because, like, it was the most impractical, useless piece of. Why did you put this in there? I don't understand it. Why? It takes more multiplies to transform by that. Why would we
you'd
do that?
never
We
do
spend
that.
all our time multiplying by a 3x3 matrix
Right.
already. We can't add more multiplies.
Okay, so let me pause for a second there. So what year is this?
This would be like 88 probably.
88.
Yeah,
Okay. So
87,
let me see. So 88. Let me ask John. So in 88, you're at Origin.
Yeah.
Yeah. Okay. Okay.
Yes.
When? Just so I make sure I kind of.
So, hold on a
get,
second. Am I the youngest person on this panel besides you? Because that's never happened to me in my time.
yeah, I think so.
I'm 46, P.S.
It's a living history panel.
For a little while longer.
So, at what point, just so I can line these up as we go through discussion, at what point did Origin start thinking about 3D graphics stuff? So I have that in the right, because obviously doing much of Ultima stuff was around
there was no 3D content in the Ultimas at that point. I would have been working on Ultima 5, transitioning into Ultima 6. We were finally leaving the Apple II behind. There was a lot of wailing and gnashing of teeth about that, but we got over it. The first appearance of 3D kind of happened shortly after Chris Roberts showed up, looking for someone to publish a 2D role-playing game that he was working on.
is this a game that ever got published?
No, this was a game called Times of Lore. It's not a very well-known game, but it was kind of a roguelike 2D platformer almost. But Chris really wanted to do a 3D game, and he ended up pitching Wing Commander at the execs at Origin, and no one really believed it could be done, just because something like that almost requires texture mapping.
And can you give a little bit of a background for people who didn't see the original Wing Commander, what that technology was? Because I remember it because I played it.
Well, Wing Commander was kind of an interesting technological problem because it wasn't actually. It looks like it was texture mapped. It looks like a game where you're flying around in fully rotated and scaled and oriented. Bitmapped ships and shooting at other ships, that look the same way. But at the time, I think a 386 machine was the latest and greatest thing on the market. I remember Chris's compact 386-20 machine. I think he paid like $15,000 for that, if I remember right. Basically, there goes half his royalties from his last game, right? But you didn't have, you did have a multiply instruction, but you didn't have much more than that. And you had really slow main memory. And you also, more important, you had a bunch of people who really didn't know what they were doing. So Chris ended up writing, I think it was around 14,000 lines of x86 assembly code to do what's called a forward transform mapper, which works completely differently from anything that we've later come to understand as texture mapping, but is conceptually it's another way to get to the same. It's another road to get to the same destination. Texture mapping starts with,
Do you want the pen?
No,
Okay.
well, maybe later.
Okay.
The idea is you map pixels on the screen back to source pixels in your texture. That's what everybody tends to think of as texture mapping, and that's what you might call inverse mapping. Forward mapping has some advantages in that you're stepping through basically each horizontal line in your source artwork and figuring out where it goes on the screen. So This ends up being faster for shapes that have a lot of transparency, because you don't spend a lot of time jumping around pixels that you're not drawing. But it inevitably turns into just this hellacious collection of special cases, which is why it was like 14,000 lines, and why he looked like he was ready to, bring an Uzi to the office. He was really on the edge there by the time he finished that. So that was kind of the first attempt at texture mapping, and it was wildly successful. But it doesn't generalize as well as true, inverse transform texture mapping. And that was when we started looking at the Strike Commander technology that came after Wing Commander, and that would have been in the very late '80s, early '90s.
Okay, so now that I've got those two, I'm going to kind of go through. And also, when were the texture mapping articles, Chris? Because those are kind of the cap of like, here we've kind of got
April
it.
'95 is the first one.
Okay, so this is a pretty big span of time, actually. This is like from '88, did you say, to '95?
Yeah.
Okay, so it's actually 7 years before it's kind of like.
What was SGI doing at the time? They had hardware texture mapping.
Oh, yeah, for sure.
They had like really nice filtered, like, so.
It was known how to do all these things.
Yeah.
You just couldn't. You didn't have the
We were
performance.
looking at the flight
to do it
simulator. The
on
flight
the
simulator
screen.
hardware at the time had texture mapping, but it was essentially done on video scan out. Those machines actually
Right.
didn't even have polygon rendering and rasterization.
Right. But towards the early '90s, they got texture
that.
map
Yeah,
triangles
yeah.
in an iris or whatever. Yeah.
Okay, towards when, do you think?
I think the early '90s, late
Early
80s.
90s,
Yeah, it was
okay.
right around that time because
All right.
I mean, we just didn't know any of those people,
So-
and we didn't
Yeah.
pay any attention to them, and so they knew exactly what they were doing mathematically, and we had no idea.
Can you talk a little bit about that? Actually, anybody here who has some opinions about that? Can you talk about, because at that time, and possibly again due to sort of the fact that the internet's not really a thing, the relationship between those communities. So I guess what you're saying is there were people who had done the research on this sort of stuff for hardware or
Well, none
for
of the books published it.
offline.
I just read I hadn't read my articles since April '95, and so I just started. While you were trying to get the PowerPoint viewer going, I was like, oh shit, I better read some of this. And the beginning talks about the lack of information in books, like Foley and Van Dam didn't really cover it very well, and it disses Sean subtly without naming him.
Foley
I didn't
and
know.
Van Dam does?
No, my articles do,
Oh,
because it's like, and you
okay.
can get these text
Thanks,
files
Chris.
off like x2ftp.ou, like, but they're totally incomprehensible with no
Okay.
working code. I was like, oh, that's Sean. We didn't know each other at the time.
And Sean, when did you first post the text file? Because I'm going to talk about that later as well. So
It would have been 93 or 94, I'm not positive.
okay, so
Was that post when was Underworld?
Yeah, it's after Underworld.
Yeah, because that was about the Underworld. Ish.
I got into it because of Underworld.
Right.
okay, all right.
Were
so
you
I think
there?
we've got
Were
all
you
that.
at LG then?
I was contracting. I visited a few times.
Okay.
So let's jump back then now so we get it. Okay, so we're in 1988. We are looking for ways to add sort of more
Yeah.
detail to the flight simulator.
Yeah, without more polygons.
Without more polygons.
Those are expensive too.
And essentially, we, at sort of similar times, people in other industries have been working on texture mapping stuff, but in general, like, why is there no understanding there? Is it because you don't even necessarily know that these other people are working on this sorts of things, or even who you would ask kind of stuff? Like, give me a little bit about that, because most people can't probably relate to that, because nowadays you just type it in the internet and go,
Yeah.
right?
Yeah, just you were talking about getting information.
Yes.
All my graphics information at the time, I had to get on my bicycle and drive to the Stanford Library and start Xeroxing stuff, which I generally couldn't even find what I was looking for. So I literally just go and just look through journals and Xerox.
Wow.
I'd come back with a pile of whatever looked interesting.
Yeah,
and
I had
try
that same pile.
And then I didn't have the math background to figure out most of it, so I would just stare at it over and over again until I kind of figured it out.
I think John mentioned that earlier, which is like, there's the like, oh yeah, this hardware was crap and blah, 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 but also we just had no idea what we were doing. And it would be really interesting, given the math knowledge that's pretty standard among engine programmers now, to go back with the shitty hardware.
the
We could do
critical
way
thing-
cooler stuff, I think, just
Oh,
because.
absolutely.
The important thing back then was that we weren't any good at math,
Yeah.
but neither were computers.
Yeah.
Right.
Your whole, the whole goal for, from the morning when you got to work, from the time when you leave at night, is to figure out a way to avoid doing math.
Right. But you can avoid doing math by knowing math, which we couldn't do back then because we didn't know enough math to not do it.
To some extent, yeah. But also, I mean, you don't spend a lot of time, if you don't know the right way to do it, you don't spend a lot of time beating your head against the wall trying
Totally.
to convince the machine to do it.
Right.
You know, at 1,000 cycles per pixel or whatever
Yeah.
the really
I just think that
hardcore
knowledge,
stuff
and this is the thing that would be a takeaway from the thing, is I think the knowledge would really help, even in a constrained
No,
environment.
no
Like,
question.
yeah.
Well, you see that sort of thing with the demo scene stuff, where they've gone back to very old hardware and done things much better than we
Right.
can do now,
Yeah.
because we know so much more about the platform.
Well, and there's an anecdote from the Foreman Acton books, the numerical methods that usually work book, where he's like, these engineers came over, it was at the beginning, like they had to invert an 8x8 matrix, which back then in the 40s it was like, oh my God, this is gonna take us months. What do we
Invert
do?
an 8x8 matrix.
Yeah, yeah.
That's, okay.
Yeah, they're just like, oh, there's just no way to
Because
do
they're doing it by hand.
Yeah, I mean, it was,
Okay.
well, they were using rooms of computers, which were women at the
Right,
time,
right,
like,
right,
who would
yeah,
do these
I
tables
remember
and stuff.
this.
And they came to him as the numerical analysis guy, and he was like, they're like, we need help with this. You can't get the state. What do we do about this matrix? And he does a bunch of math, and he's like, okay, well, wait a second. And it was orthogonal. All they had to do was translate.
Oh, yeah, I had to do
Translate it. So like it was like he's like, wait, the inverse of this. So they invert it on the like it takes hundreds of hours of computer time. He's like notices this thing. He's like, if you just had like actually written out the equation, and like so that kind of thing happens a lot once you've got the overarching math knowledge. And so I think that you could go back to these texture map
Yes,
processes and be like,
absolutely.
way better.
Although the other thing too, one thing that's kind of interesting about it is sometimes having a lack of knowledge does lead you to a solution
Yeah,
that you
totally.
couldn't have thought. So
Which
it's
is
almost like
where
you
I
would
was
like
going,
both.
yeah.
You'd like people who don't know what they're doing.
Yeah,
right
you need
now,
a clean
and
room
people
do-
who they
people
do
who
know what they're
completely-
doing,
yes.
and then you see it just someone at the end
You
kind of
just
mixes it
sever your
together.
corpus callosum and like
Okay,
you have one half of
so-
your brain.
No, I think there's a chance that if another thing that some of us might have rejected the solutions we came up with as too imprecise,
Right.
could
Yes.
never work, it's too,
Right.
it's too.
But when you try it, you're like, it looks better.
it looks way better than nothing.
Yeah, yeah.
And I think that's also part of the problem here too, is defining what you're trying to achieve is difficult because if you look at old games, they're super shuddery and shaky and
Yeah.
but it's still that's as good as it could look at the time, you know.
Well,
So
it's like Chris was saying, we just wanted
Yeah.
stuff on
You
the
just want
screen,
something,
just like
yeah.
like that line is kind of grass. As long as it
Yeah.
moves in 3D, like it'll
Yeah,
give some kind of
exactly.
thing.
No, I was looking for screenshots from Car and Driver this morning that showed some texture mapping on them, and mostly what I saw is like patterns of like colored dots.
Yeah,
It's
yeah.
like super low resolution screen, but it's better than what would have been there, which
Yeah.
is just white.
Yeah.
So okay, so let's keep going. So in 88, looking for texture, you tried, and so it sort of sounds like what you tried doing first is taking rectangles and subdividing them. So
Yeah, I tried
can you explain a
recursive.
little bit? Just explain the mental process there, if you can remember. Like, sort of why was that what you're going? Is it because a picture is a rectangle, like a bitmap is a rectangle? Like, what were you trying to do?
Well, so again, I've got a two-dimensional image, which is a quad, and I've got a three-dimensional quad on the screen,
Right.
and now I just probably did the inverse mapping. It's simple, right?
Right.
I'm like, how could you even figure out which pixel would go where? I know the ones that are at the corners,
Yes.
which ones are in between. Well, I know which one goes in the middle. Okay, I can follow that to its logical conclusion. And also, I didn't know how to clip it, and that would work too.
So
then
did you affine map it? There's that one.
Yeah,
Like, did you
yeah.
just you average to find the middle pixel?
Yeah. Well, and it would basically say, hey, is my rectangle smaller than a pixel?
Right.
So subdividing
Yeah.
it. I mean, stop. What do I subdivide?
So it never occurred to you like, oh, it wouldn't actually be the center pixel. in
No,
the
I
center.
knew. I mean, I
Okay.
was wondering even what I would see.
Right.
Yeah, I knew it was going to kind of be wrong, but
Right. But did you know that it was going to be wrong perspective warp-wise, or
no,
just
I didn't
wrong
understand.
'cause I don't know what I'm
I
doing?
drew pictures and I said, oh, well, of course it'll perspective warp because these edges will shrink and this edge will still be tall, so it'll look like that.
Can
Perfectly
you
right.
unpack that for a second? So
Well, it's just like if you've got like if you
well,
look,
do you want to draw a diagram of the perspective?
I mean,
mapping here?
everybody in the room, except for the people facing exactly forward, I mean, this side of the screen is smaller than this
Yes,
side if
yeah.
you're fitting on this side. And like, if you subdivide the screen right in half, it's not going to be halfway through the quad that is the center, the texture you're mapping, because there's perspective is happening. The same thing that makes it smaller shifts everything in a certain direction.
And this was, I guess, the point to bring up there is this was unknown to the people working at this at the time generally, because you're sort of thinking of moving, just sort of putting this
Well,
image
as soon
on
as
the
you get one
screen,
working, you
smush-
see it because the thing warps
yeah,
like a
exactly,
bubble,
yes,
right?
but it
Which is
wasn't
like,
expected.
Right. I mean, it's kind of like it's kind of like the quaternion thing that you were like, you can just average these because
Right,
guess
right.
what? The warp's not that bad part of the
Yeah.
time.
Right.
But when it's visual, you detect it a lot more than, say, a rotation.
So continue. So you tried that, and it works, it sounds like, but it's too slow.
The perf was insane, ridiculous.
Okay, yes.
Yeah, I showed it to people. It's about all it was worth.
And then when was the next time you tried working on
Well,
something?
so I tried the blitter thing. with
Okay, the blitter thing was
horizon,
after that, okay.
targeting explicitly drawing some hills or something on the horizon.
Yeah, so I was
Because
gonna
our
ask you-
horizon's a straight line, right?
Yeah,
It looks
yeah.
kind of boring
That's true.
in a flight sim.
Did you try and pile up lines?
Yeah,
Okay,
exactly
that's
that.
why you were saying you were getting gaps
Yeah.
because you didn't know how to like offset it right.
Yeah, I could do it now.
Yeah.
I don't,
Again,
maybe I'll go back and get one of the emulators tonight and
Totally.
see if I can make it
That's
work.
a good use of your time.
Finally.
So then what? Because I think it's
So
still...
then I left there. I did a couple flight sims there, and I went out and I worked, moved to California, worked for this guy, Ned Lerner, who was doing a lot of games. I'm sure a lot of you have heard of him. He was one of the co-founders of Looking Glass, and I worked on flight sims for him for a while, and then started doing a game called Car and Driver, not that well thought of, not that good. It has thing, but we were trying to get better graphics in it, and we wanted lane markings. But the big thing was the VGA came out because we've been working. The PC, all the games I did before were these 16-bit color, 16-color games, and particularly not even the number of colors, but it kind of put you in a mode of
You couldn't
thinking
set
about
the
it.
palette, could you?
You couldn't set a palette. You said 16 fixed colors, but on that system, it was designed to write scan lines, of sequential blocks of the same color. It's really like it's almost like they designed it to fill polygons. They didn't, but it was very good at filling solid polygons. So hard to do. And so particularly, there was this crossing point when the VGA came out. So EGA, everything before that, all the 8-bit machines, you never did any graphics where you did instructions for individual pixels.
Okay.
You blitted, you shifted some bits and you wrote 8 pixels. On the EGA, you wrote to one register and out come 4 pixels, et cetera. And it was, it's kind of impractical. There's a lot of pixels on the screen. The 6502 only is a 1 megahertz processor. It's got a lot of, there's no way to do it. The original IBM PC has nowhere near, but eventually the 286 and the VGA meant that you kind of had to do one instruction per pixel on that system anyway because they were bytes.
And so just for people who aren't familiar with this kind of programming, I'll just unpack that a little bit.
Yeah, for sure.
So basically, nowadays you kind of think of the graphics card as something you sort of ship instructions and stuff and data over to, and it does some work. But of course, at that time, the graphics card that's in, say, a PC of some kind is really just something that you're kind of writing to memory. The CPU itself is writing to memory on the card indirectly, and that writing is happening like a pixel at a time. Like I need to set this pixel to this color and this pixel to this color, and just off you go. So you were sort of saying the EGA style, or the pre-VGA, when you did that right to the card, you had to fill a bunch of pixels at a time because that's the way it just got sent, right?
Yeah, and for perf, it wouldn't practically, but there's a crossover.
On the VGA, you could send them one at a time.
Yeah, and so once you're on the VGA and you maybe have like a simple memory fill operation for 16 for every pixel in there, you start to think, well, I could probably fit another instruction in there and 1 or 2 more. And so we tried to do some stuff. The first thing we did was, and a lot of games did this. I don't think we're the first on this at all, but we did bitmap scaling, where you could basically take an image, and size it on the screen dynamically, and we would use that we used it for clouds. The first thing we did. It doesn't really work in a 3D game because as soon as you start turning like that, but that was our first thing, and we basically iterated from that. Like, wait, we could do Garo shading, because that's only maybe 1 extra instruction, an add and a store. And then we realized we could maybe do bitmap rotation, and at that point, it looked like a few more tweaks could get us texture mapping.
Were you forward mapping or reverse mapping the bitmap rotation?
We did reverse mapping all the time. So, like for instance, our bitmap, we had high-speed bitmap scaling. This is pretty interesting itself. So you got an image in your scale to screen. It's still a rectangle. All the lines are still straight. Particularly every scan line that's output is either, if you're scaling up, some of the lines are copies of the line that you scaled before.
Right.
So when you're scaling up, you can save a lot of perf there.
Yes.
But you're going to be doing a scaling pattern where you're doing a sampling, like, oh, I grabbed this pixel, then I skip this one, then I grab the next 2, and that's going to be the same pattern on every line.
And so
so we wrote wrote code that basically generated a set of assembly code to self-modeling code to output 1 line in the current scale thing, and then it would just jump back to it.
So let's talk about that for a second, because that's actually something that I totally failed to think about, but it was very common at that time. So nowadays, typically, because of the way processors work, you generally don't want to change code on the fly because they have processor cache and all these
Yeah,
sorts of things.
pipelines.
Instruction cache on the processor. So typically when you write code, we think of it as just we write code, you compile it or whatever, and that's the code that's going to run. But of course, that's because we have all of these things like, hey, instructions are cheap enough that if you just have if statements in there or variables in there that you're accessing, it's okay. At that time, like literally every little tiny thing you might do was a cost. And so one of the things that people did, and I guess I don't know, this probably predates, I don't know when this started being a common thing, but self-modifying code is a big deal. Writing something that would just output the instructions to do a specific bitmap scale rather than a general bitmap scale would be common. So was that something you guys had done before, or?
No, but I'm sure people will come up with it.
All right, so basically, like, this was the thing where we sat down and we got to do bitmap scaling. Let's just work through the how does that process go? We got to scale bitmap.
No, it was more like we thought about bitmap scaling and thought it was impractical. And kind of ignored it until we thought of this.
Okay.
Again, we were targeting, the 386 was a high-end chip that the developers would buy for developed systems. The systems we were targeting were not 8386s. They were very low-end and didn't have any 32-bit registers or anything like that. But so once we said, wait a minute, it could probably be fast enough if we did that, then we did it. Similarly, talking more about the hardware at the time, I mentioned we did gyro shading. That's really simple. And it wasn't even hard then, except for one thing. So nowadays, your screen lets you have any RGB pixel you want at any location you want. And you just say what color you want, and you get it. The VGA is a chip where you have 256 colors, period, on the screen, total, end of sentence. And you can decide what 256 you want to be able to choose from. But and so you can map images, and they generally look really good in that scenario. It's a good compression thing. But it makes it really hard to do calculations involving color. You can't say, hey, color 120, what color is red plus a little bit of blue? You can only do that by either making lots of mapping tables or having your palette be all black. People would take their palette and make it just shades of 16 different colors and stuff like that.
Well, yeah, I guess so people don't tend to think about this very often, but yeah, at that time, all colors were palletized.
Yes.
Meaning a color was just an index into a table, and that index may have no relationship to what the color actually was. So you couldn't just take two colors and blend them together. You had to take two color indices if you want, and you can't really blend them together, right? You
not unless,
So,
but it's like John was saying, like there was no performance to do actual RGB blending anyway.
Oh,
So it's got to be palletized.
So typically, I guess what people would do is set up these palettes so that they happen to have correspondence.
Or make tables. So like Underworld had this thing where it would darken the texture mapping farther away, and it worked by having a bunch of 256 entry tables that were like, oh, in the palette, the closest color to 25% dimmer than that color is this one.
I gotcha.
And then it would do that.
So you kind of look up into the table. I have this color. What's
the slightly dimmer version of it? And,
and
if your palette's it's not guaranteed to work. There might not be a color that matches.
But it would just give you the best guess,
Yeah.
right? I assume that table is filled with
Did
the
artists
best.
make that color, that table?
We would generate it, but someone had to.
And then,
I think our palettes, people generally did not choose like, I'll make a perfect palette for my game. They'd choose something like 16 green. But
it wouldn't exactly have been gamma correct.
Yeah, it was not gamma correct. And the monitors.
No, I just meant so somebody you'd generate the darker color, but then an artist would go and go like, that color is not as good as this other choice, or did they even
I don't remember actually.
Yeah.
I think we just generated it in code because we wanted the artist to be able to change the palette more often and not have to mess with that.
So at that point in Car and Driver, you've got the bitmap scaling going.
Yeah.
And you're sort of like, well, okay, now, if that's fast enough, maybe what else is fast enough? It sort of sounded like.
Yeah, so it's kind of like this mutation of loops where, wait, I can add rotation to the scaler.
Okay.
Wait, it's kind of doing two indices now. I could do a little fancier with that and realizing I could probably map.
So it's kind of like a slow step-by-step process of like, that was fast enough.
Exactly.
How can I? It sort of starts with one working example of something that's the most basic thing, and then it adds a little feature as it goes to see how far it can get.
Yep.
Okay, so what ended up shipping in Car and Driver then?
So in the Car Driver, we shipped all those things, a lot of signs, a lot of billboards. We tried to put markings on the road, but it wasn't performant. So there's kind of if you actually those games use a lot of same code. That and Underworld use the same kind of kernels mostly.
Oh, really?
Those operations, yeah.
Ultima Underworld and Car and Driver had the same text mapping.
I was actually working on Car and Driver and contracting for
at the same
for
time.
Looking Glass for that, and we were selling basically the tech from Car and Driver that There's a cross.
okay.
Basically, the texture mapping went, that was in our assembly language engine was taken and put into their engine. So the underlying engines are very different from each other, but
just
this
that
drawing
one-
function. A couple of
yeah.
things, yeah.
Interesting. Okay.
Oh, no, actually, no, a bunch of the engine was in there too, but we had this engine kind of based on what we did for flight simulators, which is kind of like your map format is more like, looks like an assembly language file. Meaning that like there's these opcodes, like, if the camera is outside of this region, then jump here, or draw this object here, and it had been all done at Sublonic literally by hand.
Okay.
And it's pretty effective. No, we didn't have hidden line removal, so it's full of ifs for like what to draw in front of what.
Oh my God. Okay. Yes. Right. I forgot about that.
Yes.
Okay.
But then Underworld wanted to have, it's okay for a flight sim. We used a lot of digitized data, and it was mostly heights and stuff.
Yeah.
But Underworld wanted to have a map and a map editor in particular, and a map editor that let you change things in it and had just a lot of stuff that did not suit up for that. So essentially, and it had stuff like occlusion. 'Cause,
Yeah.
we didn't worry about what was in front of what about occlusion in our games because mostly it was the ground.
Okay.
And so that was so basically the C and an Underworld was changed to generate the opcode stuff for my engine,
I got it. Okay.
something like that.
So let's jump back to Origin here for a
Yeah.
second. So what's going on with we're starting to talk about the Strike Commander stuff. Where does that line up with Ultima Underworld's release?
Well, the big thing you have to keep in mind about what we were doing on Strike Commander was there's a big difference. There's a wide gulf between what we're calling affine mapping, affine mapping, I'm not sure how you say it, and perspective mapping. Perspective mapping is what you need if you want to draw one polygon that shows perspective across the single polygonal surface. It's much harder, needless to say, it's much harder to do that than it is to just do a simple two-dimensional Bresenham solver to do a simple 2D affine map like flight simulators tended to do. We were able to get the inner loop in Strike Commander's texture mapper down to like 8 or 9 cycles on an early Pentium or late 486 class machine. But the per pixel divide instruction that classically you would want for a perspective mapper, that alone would have probably taken 4 times that much time just to do the divide by Z at each pixel. So it just wasn't going to happen, and that's why, I mean, you have to remember that Ultima Underworld came out around the same time as Doom. I guess it was, how much later was it? Or?
Underworld was 92, Doom was 93.
Yeah,
Okay.
I think Underworld was first.
Yeah,
and then Doom.
Underworld was actually first, and what was amazing about that is that it was almost right. It almost actually had full perspective mapping. Chris cheated by doing it perspective in I guess
I did something special for the walls.
Z direction, but not in. If you go back and play Ultima Underworld, and then position yourself next to a wall, you get this crazy warping effect, which some of you may have noticed.
So was that not just a straight affine mapper? It was something weird? I thought it was just a subdividing.
It was
There was
perspective along the
there were
scan
multiple
lines.
things in it. It would subdivide in 3D.
Yeah.
It would do this thing for walls where I would actually calculate the column right. I realized that they were in columns, but Underworld could shift the screen.
Right.
But I didn't even understand actually how to solve for what columns, how to inverse map that. So I had this thing where I'm like, wait a minute, wow, I know what I'll do. This only matters when things are blown up, right? Because when they're small, the effect's not that big. So I basically forward mapped it because I knew how to divide. I knew how to do perspective divides, but not how to invert them.
Okay, so let me unpack. There's a lot in there.
Yes, I'm sorry.
First of all, let's start with one thing, which is that, so the interesting thing here is you mentioned Doom. So Doom does not allow you to.
But Doom's perspectively correct.
It's
but
perspectively correct.
But you can't because you can't.
But you
tilt.
can't turn your head, right? So that kind of line
But
sort
that's
of
a
fix this problem.
classic Carmack thing, which is like, fuck those general problems. I'm going to solve this other problem perfectly.
It's all about
Right?
not doing the math.
Yeah.
We were still at a point in time
Right.
when you won by not doing math.
Right. So
And,
it was
and that's completely different now.
It was a great knee of the curve, like. Thing.
Yes,
Whereas,
certainly.
I mean, looking
But I
glass
was
was
gonna say-
totally this opposite thing, which is like, no, we have to be able to walk through this dungeon.
Yes, yes.
And then, like, you're walking and your
around,
head's
yes.
bobbing, you look everywhere because there's.
That's why those of us who were in the industry were more blown away by. I mean, we were blown away by both Doom and Underworld, but I personally was like, having actually tried some of this, I was more impressed by Underworld just because they were, so much earlier than anyone else doing, a real dungeon.
They were just different. I mean, it was just an interesting engineering approach to two different things. I mean, Underworld, if you recall, was also a tiny window on a 320 by 200 screen. Yeah.
That was
So-
the best we could do on the
Yeah,
TV
yeah,
things.
exactly.
So, in Underworld, just to be clear on that, so in Doom, they solved this problem by just fixing the screen. And the reason that that's important, just, to try to get that out there, is if you know that all of your perspective changes happen in vertical lines, obviously you can make a bunch of optimizations in terms of what you're doing that make it not matter as much. But in Underworld, you could turn your head for real. So the world would rotate like a modern 3D game rotates, which now means that the texture mapper has to handle anything. It can't assume that vertical lines are where the perspective goes.
If you
So-
care about the perspective warping, and the thing is, in a dungeon crawler, both Doom or this, the closer you get to the wall, the worse the affine, because the more the distortion happens. So you just get this, like, it looked like the wall was about low.
Yes, exactly. So what I was going to say is, so that's
Which is why in a flight simulator, when it's a bunch of polygons on a 3D object, the vertices are going to be correct. So a rotating, like, spaceship or airplane doesn't matter. It's just affine map it, and you don't care.
So, so anyway, just unpack that. So the problem when you're looking up and down is now you don't have these convenient sort of vertical lines of perspective change. So when you're doing the mapper for this, I wanted to unpack some of the things you were saying you tried. So you've got these sort of large wall tiles, because again, everything at this time has to be very low poly because just the transforms of the vertices costs you plenty of work as well. So you can't afford to just have really densely tessellated stuff, because that would have solved the problem as well, right? Like super densely tessellated geometry would have been fine, but then you'd get killed by the transfer. So here you've got large polygons on the screen. You're trying to sort of get rid of the warping that happens there, but you're not really necessarily sure exactly the math, right?
I'm not exactly sure where all the warping comes from.
Right, so, yeah.
I remember drawing a piece of graph paper and drawing walls and columns on it, and convincing myself that it wasn't affine vertically, that it was only close, that there was some warping that I didn't understand. I mean, I convinced
That's
myself of the
interesting.
wrong thing.
It seems a lot more complicated than what I was assuming. I was assuming that you were always perspectively correct at the scan line endpoints.
No,
but
I
then
had a lot of
affine
problems because
along
of doing clipping in 3D, actually. That hurt a lot, because essentially, you got your polygons are halfway off the screen. You've got to find the corner points. And a lot of people would do 2D clipping or hybrid ones where they would just kind of like skip, some polygons a little bit off the screen. They don't 3D clip it, they just don't draw the pixels that are off the screen.
I see.
But because of texture mapping, I needed the UVs, which I didn't quite understand at all.
Yeah, there were
and
no
so
UVs.
the problem is
Were
then
they-
you end up clipping, if you do that, so the clipping is actually perfectly mathematically correct, absolutely. But what ends up on the screen isn't. And so you get these effects where, imagine there's a wall like this, and it's just sliding off the edge of the screen, and it's not quite mapped. It's got perspective distortion. The problem is that perspective distortion starts shifting
As you correct, 'cause the
and
clipping
you
is
literally
correct, but
watch
the
the
end-
texture
yeah.
swim because it's getting the wrong coordinate. And so we would take large polygons. We'd fill a big wall like that. The first thing I would do is I'd say, wait, there's a big wall. It's close to the eye. That's the thing that always looks bad. I don't quite know why, but
Did you guys have UV coordinates? Did you even understand? Okay,
we
you
did.
Okay.
And so I would take that and cut it into 4 polygons.
Because like Sean's original paper didn't have UV coordinates. Like another breakthrough conceptually was the idea of like
We'll
I
get
have
to it.
coordinates
Yeah, I
in
got a
the
PlayStation
texture. What's
installed.
that?
We'll get to it.
Yeah, but I mean, it's,
Chronologically,
but right, yeah. It's just this idea of like you don't have to use UV coordinates. You can use a plane equation that just describes where all the pixels are.
It
all the time.
describes the UV coordinates, though. It
Right,
does,
but I'm just saying we didn't understand
Yes,
the math
yes, yeah,
and that
That
quote
was
unquote
my
breakthrough.
whole point, was
Yeah,
to just approach it from math.
yeah.
Well, we'll talk.
Okay, so yeah, let's. So I just want to finish the Strike Commander part as well, though. So
Well, Strike Commander was later though, wasn't it? It was way post.
Strike Commander
Strike was early.
later than what?
Oh wait,
Well, I'm trying to place
because
it.
you were saying 46 in Pentium, but it's just way before, way after.
Wing Commander shipped right as the 486s were coming out, I think.
Oh, did it?
If I remember
the
right.
Strike Commander did.
Around,
Or what
no,
Wing
Wing Commander I guess would have been around 91 or so.
Yeah, so that would have been a little pre-Underworld.
Yeah, and then Strike Commander took a long time for reasons unrelated to texture mapping.
Right,
but it,
It's actually, it's funny you said that because it's hard to actually, like, it was just the topic you talked about. Like, you'd be at GDC, CGDC back then, and you'd be at a dinner table with a bunch of people, and all you'd talk about was texture mapping. Like, okay, so we tried this other thing. Like,
Right,
it was
it was
literally
a huge-
the only problem to solve in video games.
Yes. So just to ask a question about the strike rank thing. So can you just give us a little bit of background, because we didn't really talk about how did that come about, right? So you had Chris Roberts had done the crazy 14,000 line of code affine mapper for Wing Commander. That shipped, I guess, potentially a little bit before Underworld or something, but obviously has nothing to do with the sort of stuff that Underworld was doing.
Right.
It is, I guess, sort of a little bit more like the stuff that was doing in Car and Driver, even though the algorithms were different. So now you're looking at that and going, we want to do real 3D, I guess, because I guess the thing we didn't talk about with Wing Commander is, with Wing Commander, yeah, you can rotate the sprites this way and you can scale them, but you can't do anything in, rotate this way. So what it would do is it just
you had to capture all these pre-rendered
pre-rendered
views,
views, right.
and then select the one based on the your
orientation.
vector to the ship that you're rendering.
So what would happen there is you'd see these, as the ship, be super smooth rotating this way, and then as it would rotate this way, it would be like clunk, clunk,
Yeah,
right?
exactly.
So I assume, is that the impetus behind sort of this? Like, can you talk a little about like what you were trying to do, how you approached it, what happened there?
Around the same time, I think, if I remember right, LucasArts had a game that actually did full texture mapping first. It didn't have all the nice shading options and other options, but it basically was like a bucket of cold water in Chris's face. He wanted to do this space game first, and he was happy with it, as he should have been. But for doing his combat simulator follow-up to Wing Commander, once he saw I think it was Secret Weapons of the Luftwaffe, something like that.
Yeah.
Once he saw that, he realized that we're going to have to go to texture mapping, or our cool combat simulator is going to look like crap. So that's when he, there was sort of an informal competition that kicked off among people at Origin and people who had recently left Origin, meaning me, to get the fastest inner loop for a simple affine mapper that's suitable for use in a texture map flight simulator. So we went back and forth, and the person who really should be here is Michael Abrash, whom I'm sure a lot of you know. Michael couldn't be here, but Michael had what he really contributed at that time was he was writing all these magazine columns describing for the very first time in easily accessible public print how texture mapping worked. And he would provide a lot of example code. This was in a defunct magazine called Dr. Dobbs Journal that everyone in the industry subscribed to at the time, hugely influential. I saw the work that Michael was doing, and I realized, this is how actual general purpose, texture mapping works, which is something I'd never really got before. So that kind of kicked me off on the whole, his code takes like 30 or 40 cycles to do one pixel, and then eventually it goes down to 20 when I'm messing with it, and eventually I get it down to 15, and somebody at Origin has it running in 10, and we're like we have this friendly little pissing contest going to get every last cycle out of that inner loop. And
Well, do you want to tell the funny anecdote about that? So Mike, I was at Microsoft, worked for Mike, he was my boss at the time, and or right before that, right after that, and like he had heard John had a 9-cycle version, and his was like 14 or something like that. He's like, well, fuck that. I've got it and he got an 8-cycle version, but John didn't ever have a 9-cycle version.
So he had just heard someone say
because knowing something's possible is a
all it
huge
takes.
part of the thing.
And there's a whole chapter in his big black book of graphics programming on that exact experience that Michael and I had going back and forth with each other. And he makes the very good point of, he wouldn't have tried if he didn't think someone had already beaten him. And I wouldn't have had something to shoot for if he hadn't published, the 40 cycle per pixel version or whatever. So just having that existence proof in place is
or not,
or the existence lie.
Exactly.
The perception of an existence.
And then later in a file that's probably too obscure to really bring up on a screen here, Ken Silverman, the guy who did the build engine, most famous for Duke Nukem, he got it down to was it 4 cycles per pixel, something like that?
For an
Do you,
affine mapper?
I can bring up the
Yeah,
text document.
We could, I don't know how enlightening it'll be.
Yeah, it'll probably be.
but,
Well, I'll just put it here for
But
For amusement?
so I was kind of out of the game by then, but there was Ken and then there was Dave Stafford. I think probably Stafford is the one who got it down to 4. I don't remember.
Yeah, I don't remember. Because people switched to perspective at one point, and then you had to subdivide, and then the cycle counts went back up.
Yeah, we're still talking affine.
Affine, yeah.
But I believe, basically all the stuff that I was doing all this chest thumping over, getting it down to 8 or 9 cycles or whatever, Ken was at the same time, more or less, Ken was getting it down to like half that. So there's always another cycle.
Yeah.
You can, whether it's worth going after, maybe not.
All right, so let's I guess move forward a little bit. So eventually, because I kind of want to talk about the second half of this process. So Sean, tell me a little bit about, because Chris was at Looking Glass earlier, and then you came to Looking Glass, I guess it was around System Shock time? Or that's in between Underworld 2 and System Shock, roughly?
I came in '94, and System Shock was basically done when I got
Okay.
there. They hadn't shipped it yet, but it was
Okay.
basically done. So they had done all the work on like the texture mapper.
Okay, so let's talk a little bit about that process. So basically, like from Underworld to System Shock, they've kind of gotten to the point where the perspective stuff is under control, or not really. Like, give me a little bit of background on like what happens at Looking Glass during this period of like, okay, so Chris has got the first one going for Underworld, and then they've gone through kind of 2 iterations.
They-
I think
Underworld
Kevin
2
Wasserman was the person who did some of the work on this. I never was able to find contact information. He's the only person I couldn't invite. But yeah.
Underworld 2, I don't know really any of the details. Just as a user, I could see that the mapper was different. I don't know whose work that was.
Okay.
It looked like the main thing was that for the perspective mapper, they split quads into 2 triangles and just drew 2 affine triangles.
Oh, okay.
Which meant they were all straight lines across the triangles. There were
Okay.
no curves.
Okay.
But you would get this weird split when that was a perspective thing. You would have the seam and if you draw a grid, the grid lines wouldn't line up across
okay.
the diagonal. And then for System Shock, so there wasn't really a lot of stable technology. They just kept, here's the newest current thing.
Okay.
Part of that is because the machines kept evolving.
Right,
And-
even the instruction set is changing
But
during
even,
this time.
but even
right?
without that, the microarchitectures being different meant the performance trade-offs were different, which meant the thing that was a fast loop on the 386 wasn't going to be the fastest loop on the 486.
Got it.
And et cetera. System Shock, the main thing that they did was that they did have a solid perspective mapper without warping, and without cheating.
Okay.
Which was done with what was called a lines of constant Z mapper.
Okay.
Which involved, so
I
in the
forgot
normal mapper, you would draw scan lines. You would do this inverse mapping, and you would process a single scan line of the polygon.
Right.
And because it's, when you had floor mappers and wall mappers, that was a constant step, an affine step in the source texture map.
Okay.
So you could just trace that along very efficiently.
So what you're saying, sorry if I could get
Yeah.
that right. You're saying that walls and floors are special.
But that was the Doom
Well,
optimization.
the lines of constant Z on a floor, if you can't tilt, is a scan line.
horizontal.
Regardless
lines-
of how you go this
No,
way.
you can't.
You can't,
You
you-
can't-
the floor
well,
you
the floor
can't.
you
Floor
can, but then
you
the
can, but the
walls are
walls you
tough.
can't,
Yeah, yeah,
right?
yeah.
It doesn't help because the walls, the lines of constant Z are vertical, and if you
Yes,
tilt that, no
that
longer
changes,
is
right? But the reason that floors and ceilings are special that way is because the rotation doesn't affect that plane, right? That it is the same. I don't know how to say
Yeah,
that
it's
properly.
the intersection of planes. I
Yeah,
think,
yeah.
So it's a little complicated.
Okay, but so walls and floors, we're using this already, I guess is what you're saying?
Well, so the idea there is that Doom was already doing
Yes.
all of that. Like,
Okay.
just relied on that, and that's how it was perfectly perspective correct
Okay.
by restricting the world and the player in such a way.
Okay.
So I don't know the exact details. Chris said there were multiple mappers to handle those cases, so they could be faster and more correct looking in some of those cases in the Underworld one. So in System Shock, they introduced this lines of constant Z mapper where there is some, on a polygon, there is some on-screen line that is a line of constant Z across that thing and will be at every offset.
Meaning
from-
that along that line, it never goes into or out any further back or closer to the
Yeah.
viewer. It's
Yeah.
the same distance from the
And you
viewer.
don't
If
along
you
the
had a
line.
divide
Z
or
buffer, it would be the
multiply.
exact.
Yeah, I mean, just
same
take a
value
plane
possible.
and slice it through your world, and there are your lines.
There's
of
your lines.
constant.
Yes.
Like when you're doing the thing of looking at the wall, and you tilt your head,
Yeah.
those lines are still straight lines that are still affine. They're just not
Right,
aligned
they're
with the
just
screen
with the wall.
anymore. But you can render in that along a diagonal.
Got it. And so that's the System Shock tech, is the lines of constant member. I guess one thing I should ask this time, when did that concept of having multiple mappers start coming out? Because it sounds like you were saying perhaps for Underworld 2,
Underworld 1.
sorry, even Underworld 1 had
Yeah,
this?
yeah.
Okay, so can you
There are a few
talk about that
different
quickly, because we don't really talk
Well,
about that
Doom had
anymore
multiple
either.
map, and the way
Yeah.
you did things back then was have all the cases.
Yeah, I just want to say, so could you?
Yeah, we have
tell
special
the-
cases for scaling up and down too.
Okay.
Yeah.
So basically what would happen is there's a whole bunch of different kinds of mappers. There's something, I'm assuming this process comes about because you're optimizing the code. You realize you could make an optimization if one thing was true. So you're just like, okay, can we test if that's true and then branch to two completely different versions of this
Yeah,
loop?
or similar, or different loops for little tiny sections of polygons versus long ones, because it's worth inlining if you're going to feel like
Unrolling.
Unrolling.
Yeah, yeah.
Gotcha.
But that's not a texture mapping thing. I mean, the audio
Yeah,
mixers did that.
That's,
Yes,
anything. That's anything. Yeah.
Okay, so Sean, so as far as coming on around the System Shock time, one of the things that you did is this text file that kind of got,
Right, that was before I did Looking
Oh, that was
Glass, yeah.
before Looking Glass.
Yeah,
Okay, so can you kind of give me some background on that and how that kind of got, because this is one of the first things that, at least I know, that's like publishing it out in the game industry, kind of what texture mapping even is for people who, didn't know it, and along with like sort of Abrash's Dr. Jobs journals, I don't know what they were, but can you give us a little background on this?
So I'd been reading journals and stuff in the library.
What library, by the way?
Well, this would have been back in Maryland,
Okay.
earlier, and I was mainly following the non-real-time stuff. And I really
Oh.
didn't have a good understanding of the real-time stuff, and just launched into that in '92 or so. Probably got all my information from Usenet, like, definitely read the Dr. Dobbs stuff. That was why I started doing the 3D programming, was the Abrash articles. And the frustration I had was that nobody really explained the details of what you needed to do, except the details I knew from the non-real-time stuff. But for the
Okay.
real-time stuff, I felt like there was no real, like, Abrash did have his thing, and I don't remember the details at all of that, but it just like, and at the time I wasn't scared of math.
Okay.
And so one of the things that I did is I just sat down and I said, what actually needs to be happening in the math for this to make any sense?
So do you mean at the time like you are now, or you mean compared to everybody else? You said at the time I was not scared of math.
I'm now way more scared of math.
Oh, okay.
At the time, I was in my 20s, and so
Fearless.
I could conquer the world.
Yeah.
Exactly.
Okay,
Now you know.
okay,
Now I'll just avoid it if I can. But,
okay. So essentially, if I'm getting this right, you've had exposure to the actual technical literature in terms of what people non-real, like people who are doing maybe ray tracers or something. Is that what you
yeah.
mean by?
Well, and then there were, like, a lot of people would recommend, like, this image warping book that, like, had no useful information
was
at all.
crazy.
Okay.
For what you were trying to do. Like, there was a lot of kind of bad info in that
Okay.
sense.
Well, it had
Like,
a lot of filtering stuff. If you cared about filtering or anything
Yeah.
else, none of which we could afford to
Yeah,
really
exactly.
do. But
Filtering
like,
and Paladin.
but like emit mapping and stuff was in that book, but it was definitely very not,
Yeah.
like it was weird.
Yeah, and so I kind of just said, I'm gonna solve it from first principles.
Okay.
Was what I was tackling doing. And the article tries to cover everything. So it's like, here's the math you need to know, and here's an optimized inner loop, and a single one, an
Okay.
attempt at one, whatever. So it kind of covers a whole breadth of things. And I was working on doing that work in '93. I think I put that article out in '94. And the whole point there was we had Usenet, but Usenet was actually transitory. Usenet was this thing that came and went. It was, the article came on your thing, and they kept a week of articles if you were lucky or something like that, and then it was gone again. So you had FTP sites that had various pieces of information.
Okay.
And this one guy was like, this is terrible, let's like collect all of the good information that's been going by and put it in this thing. He called it the PC Game Programmer's Encyclopedia.
Okay.
And all the information, it was probably useless a year later. But it was an attempt to put something on the FTP sites that would have a lot of valuable stuff.
Okay.
And for whatever reason, I got drafted to do the texture mapping article, and I don't know for sure, but I bet you it was the exact same thing as the Abrash articles and a lot of other columns and stuff that you read, which is the person is writing this from a position of authority, but they had no idea before they started writing the column how to do it. They just solved it while they were writing the column.
Okay.
It's experts.
So what is that process like for working this stuff out? You said work it out from first principles. Like, what do you mean? Like, again, coming at this from the perspective of like, hey, trying to solve a hard problem, you have no information to go on really. You just kind of know,
Well,
here's what an inner loop kind of looks like.
It's the other side, the math was the issue. And so it was like, we know what the 3D transform is.
Okay.
And I can characterize where in the bitmap a particular point on the polygon is in math, and just run it through the normal 3D map. So the whole thing, like in a 3D perspective transform, comes from dividing by a number, dividing by z. In some
Right,
sense.
yes.
And it turns out that the inverse transform of the texture mapping requires dividing by inverse of z or something like that.
Yes,
Like,
yes.
you know, you might think the inverse would, the divide turns into multiply, no, it turns into divide.
Right.
And so the final thing you end up with is like some math that says you have to do 2 divides at every pixel, 1 for each coordinate.
I see.
If you just sit there and crank out a bunch of math. But as Chris was saying, part of the way of doing that was to actually formalize the problem in a different way than what people were actually doing in practice. And I don't know where I got the idea of doing that from. It was like maybe the only way I could think to make the math work.
Okay.
To go through the math. And I can explain what I mean by that if you want.
You
more
certainly
detail.
can.
So the basic idea in texture mapping is you have a bitmap, and you have coordinates in the bitmap, which we call UV or ST. And you say, you have this polygon with vertices, and you say at each vertex what UV coordinate in that bitmap you want to map to that point.
Yes.
And you do that for all the points in the polygon, and you say, you know, interpolate
Yeah.
in between them. And as soon as you have more than 3 points, it's possible for you to specify a 4th vertex that you can't, there's no normal, you can't do a linear interpolation and get that result, which is why GPUs all use triangles, is because then those coordinates are planar. They're purely linear in those 2 points. But if you have 4, it's not really very well defined. And in those days, because we could only draw 100 polygons, you didn't turn everything into triangles back then.
Right.
You just drew polygons.
Right.
And so you had 4 or 5-sided polygons, so you had this problem of doing this. Now, it turns out you can take any 3 and do the math and get the right results, but you also, when you're trying to do quality things, you sometimes do this thing where you introduce an extra vertex along a line. You'll have 3 vertices on this edge.
Okay.
To join up with other things cleanly so you don't get cracking.
Oh, yes, okay. I see what you're saying. You're talking about T-junction
Yes,
sorts of things.
T-junctions.
Okay, so, yeah.
So if you do that, and you have these 3 vertices, they'll all have UV coordinates that are on a line, because they'll be consistent. And if you try to do when you go to do the mapping, you say, I need to do some math to get some stuff.
Yes.
And you do that math on this stuff, if you pick those 3 vertices because they're on a line, you get garbage results.
I see, right. So
So-
basically what you're saying is you need 3 well-formed
Well-formed,
points to
yes.
figure out the plane of this texture mapping. If they degenerate to a line.
Well, they need to be linearly independent
They cannot-
to use
yeah,
math
right,
terms,
yes.
right?
Yes.
So
So yes, if this was a matrix, the matrix has to.
if Sean
not-
wasn't afraid of math now, he would have said that.
The matrix has to not be degenerate. Is that better, Chris?
I mean, linearly independent is the correct
Okay.
word for the thing, but anyway.
And so, for example, at Looking Glass, after I did all this and I went to Looking Glass and I was talking to them, they were like, yeah, I have to I'm trying to generate the math for the constant Z perspective mapper, and I'm searching for a set of 3 vertices that are not collinear so
Yeah.
that I can get stable math out of it. It turns out there's other ways to do it that we didn't know. So.
Yeah.
So I stepped back from that problem and I said, well, I know the UV coordinates should be planar in the not on screen but in world space.
Right.
Should be planar, like they should be well defined. That once you've defined 3, et cetera. So let's
Right.
just
Because
start.
we know this thing came from something in the world that is supposed to be flat, so it's got to
Well,
be.
it's also the only way the mapper is going to work.
Right.
The texture mapper will only
Can
work
only
if
do
they
it
were
if
planar.
that's true.
So let's assume that they're planar.
Okay.
So let's just start by assuming we have plane equations for the coordinates instead of starting with UV coordinates at each vertex.
I
That
see.
was the weird thing about, one of the several weird things about my way of doing texture mapping that was in this article.
Okay.
Well, and the funny thing about it is when I was reading it, I didn't know enough math to even really know what a plane equation was at the time. And so I'm like, what the hell is this weird ass thing that's what's happening under, I mean, they're all equivalent under the hood. Like they all,
Yes,
the math
yeah,
is exactly
absolutely.
the same under the hood, but you just, if you don't have the math skills to.
And so this this article kind of makes its way out into the world, I guess at this point, somewhere around the System Shock time, or a little bit before System Shock
I
came out.
assume it was 94 before I went to looking last, so yeah, it would have been before System Shock came out.
Is this the first, like, was that one of the first ones that was published in terms of, for the game industry?
For perspective, it's the
For
only,
perspective,
it was the
yeah.
only thing.
Well, I didn't actually, I gave the coordinates, I didn't try to solve the perspective mapping problem. There was a separate article in the thing which proposed doing lines of constant z, but it wasn't.
Yeah, but I thought your
solid
thing had
solution.
like one plane equation over another plane equation.
Yes, yeah. It
You
told
didn't actually do
it told
anything
you
with
that.
it.
Yeah, he
Right,
worked the
requires
math out.
divide. It gives
Yeah,
you,
yeah,
it gives
yeah,
you,
yeah.
here's the two divides you have to do.
Yeah.
All right, and so now, Chris, this is, because I kind of think of you as being the person who codified a lot of this stuff, only because I remember at that time those like texture mapping articles were sort of the like, the final publication on it, if that makes sense.
Right.
Can you give us a little bit of background about, because you weren't working at one of the companies that was doing texture
I was
mapping
just
stuff at
friends
the
with all
time.
these people because I was at Microsoft and I got Microsoft to let me go to CGDC.
Okay.
And so I met Doug, and then through Doug I met everybody else.
Doug is Doug Church?
Church.
Okay.
Well, Doug and John, actually, John introduced me to Doug. So
Okay.
what happened was I worked for Mike. So Mike and I learned 3D graphics.
Michael Abrash.
Mike Abrash on Bix. This was before the internet.
Okay.
I mean, the internet existed in colleges and stuff.
Yes.
So right around the time he was learning 3D graphics, I was on Bix and we like kind of like helped each other learn 3D graphics together. And then I went to work for him at Microsoft.
Okay.
And then I saw some flyer that had like computer game developers conference that was posted in the like, you know, some hallway somewhere on a bulletin board, like literally like
Yes.
with a pin.
Yeah.
And I was like, oh, I gotta go to this thing. That sounds cool.
Okay.
And then
Just because you liked games, or?
yeah, I mean, it's
Okay.
just games are the cool
Yeah,
thing to
okay.
do with computers, right? So, but then I went to John's talk, which was about the texture mapper, or what it was about Eye of the Beholder 3,
Oh.
which is a video game that John just like wrote
Okay.
all by yourself, I think, right? You just like typed the whole thing in.
Did you just
I
go,
don't
yeah.
remember what the talk was.
Yeah, I don't remember either, but
Okay.
it was some D&D license, something or other.
Okay.
But you talked about texture mapping in there, I guess, a little bit.
Well, I think we actually had a sponsored session at one GDC, it wasn't a sponsored session, but we thought, long story short, it looked like we were trying to sell our texture mapper at GDC, and I think that.
Right, it wasn't. Yeah, yeah.
But-
Well, this is before I was on the board or anything like that. So I just was like this guy in the audience,
Showing up.
and like I think I asked a question or whatever, and I went up afterwards, and I was like, "Oh, Mike Abrash is my boss. Like, you know, I like to talk." He's like, "Oh, cool. Have dinner with us." And then he introduced me to Doug, and Doug introduced me to Chris and Matt Toshlag, who did Descent and all that. But so anyway, I was just friends with a bunch of these people, and so back then when I was writing those columns for Game Developer, I downloaded Sean's article. I was, you know, on Usenet and trying to figure all this stuff out, and like it was kind of the hot topic. Like I said, it was like just what you talked about when you were with people is how to make your texture mapper work better. And that was right around the time that people were trying to figure out how to go from affine mapping, which worked if you had small polygons, to perspective mapping, which is just general.
Okay.
And like there were just 8 billion ways of doing it. It was like this Precambrian explosion kind of crazy, like lines of constant z, and you know, like subdividing this way and subdividing the actual triangles, and they all had different costs and trade-offs, and everyone was trying to figure it out. And but I was like, it's similar to Sean. I was just frustrated because no one actually knew anything about what was going on. Like there was not that much understanding about what was actually happening on a per pixel basis.
So it's kind of trying to solve a problem without really defining the problem quite. It
Right,
was like, we
right.
think this kind of improved the quality of this thing because we did it and we saw that it looked
Right.
better, but we didn't necessarily have the understanding to measure
Right.
what was.
Yeah, I
It
mean,
wasn't rigorous.
It wasn't
yeah,
rigorous,
it wasn't rigorous is the best way to put it. Like it was just there was no like, here's the divide per pixel perfect code. Let me optimize that.
Right.
That's not the way it happened at all.
Right.
Which I think there's it sounds like there was some agreement earlier. Like yes, you won't get off into these crazy little areas if you necessarily strictly follow that. Like you want some, like in your simulated annealing algorithm, you want a
Yes.
little bit of heat to pop
Yes.
out to a randomization thing. But at the same time, like man, if you have that reference implementation, you can do so much more and actually understand what's going on. So anyway, I was
Well,
just
and
like,
also it never hurts to have that, even if you do want to go off into
Yeah,
the
yeah,
randomness,
yeah.
because then at least you know, here's the slow, perfect thing.
But some
so we
people
can
think that-
gauge like how good our crazy thing is versus
right.
that. Yeah.
But some people, and this may be true, feel that if you've got that, it's hard. I mean, kind of in that similar, like the
That's
nine-cycle
true.
anecdote, it's hard to pop out of that.
Because
once
you're always
there.
focusing on that way of thinking
exactly.
of the problem.
So who knows? I mean, you want both, I think.
Yeah.
But so anyway, so I saw Sean's article, and I met Sean years later. So this is the funny thing. Sean and I shared an office for a long time. But so like, but I saw Sean Barrett Like it was it PMap? We were trying to figure out what the name of the text file was.
Okay.
It was like pmap.txt or textmap.something. Anyway, but and I just could not understand a word in it. I believed that it was. I mean, I downloaded it from the internet, so it must be awesome, right? So I was like, it's on this like game programming. And so I was like, this guy must know what he's talking about, but I literally cannot understand anything going on in here. And so I was at Microsoft then doing. This is right after Doom, is a pre-Quake, there was a couple math guys around who like were really good at discrete mathematics. The biggest takeaway from this talk is you should buy this book called Concrete Mathematics by Graham, Knuth, and Podashnik. It's just the best book for all kinds of like stuff that Fabian was talking about. We were both talking at RAD the other day about how awesome this book is. Like how to move things in and out of floors and seals and like how to get rid of, just like, it's just a great.
Just to be clear, floors and seals, meaning the mathematical concrete operation of floor and ceiling, not the
if
floor
you're
and
doing
ceiling
any, if you're doing any
text
kind of
mapper.
like it's called concrete because it's continuous and discrete. Like
Yes.
that's where game math lives, right? It's going to end up as pixels on the screen or as a thing and so it's just a great book. But so there's I got turned on in this book by this guy who I think his name is Kurt. He also worked for Mike at the time at Microsoft, and I had started trying to fumble around trying to figure out this thing. And started being more rigorous about the fill conventions and how, like, what should the actual definition of the pixel actually be? And then I realized that it'd just be value. Because I'd been writing...
Just to unpack that just a tiny bit, though. So, I mean, again, trying to work through the mindset of how these sorts of things happen, why does a fill convention come into your brain at all at this point? Is this because you're working
the
on
cracks
graphics?
thing. So, like, I mean, everyone's trying to improve the look of their game.
Yes.
Right? So what do you got going wrong? You've got cracks in the polygons. Like Underworld had this crazy thing where it would like fill the buffer with purple or pink and then run random camera angles and search the buffer for pink pixels and then like print out where the camera was.
No.
Yeah, I mean, this is
That's great.
like no one knew what they were doing, right?
Okay.
Like, so, I mean, that's how you find bugs.
Yes, yes.
Right? And so I was just kind of talking to all these people and like, because I wasn't working on games myself, but I was working on WinG, which was the game library before DirectX that we did. And so we ported Doom to that and like, it was the thing, people were trying to improve the quality.
Right.
And it was like, oh, well, perspective is a huge thing. Making sure your cracks don't, if you're ever gonna write a triangle rasterizer, you want to get your fill convention right. That's one thing Mike was really rigorous about early on. Although he was, so once you add
And
text.
fill convention is just which pixels are in the triangle and which
Yeah,
aren't.
exactly. And when they share an edge, like you got to
Yes, they
decide
have to
who
line
gets
up.
which pixels
Yes.
and all this stuff. It's all stuff that the hardware mostly handles now, but like you've got to, back then when you were doing it, you had to do it.
Okay, so people in the industry generally knew that these were problems because they saw them, right? They had the cracks, or they had, but they didn't necessarily know why.
It was a hard problem. It was an uninteresting problem, even,
Yeah.
and so we all blew it off.
Okay.
And so we all had cracks in our
Got it.
walls.
But it's hard to. Go on.
Except Doom 93 was sub-pixel correct.
Right,
subpixel
right. So
correct.
subpixel is another thing. It's once you start.
perfect.
Once
And
you
what-
start.
Do we know why that was? Because like when Carmack was working on this stuff, did he just not talk about it, or did people not realize that solution would also be something you could work?
Well, no, because
through?
it was such a
drawing
special
polygons.
case. Like it was so special case that if you're trying to do a general mapper, none of the tricks he was doing
Yeah,
were going
he's
to
not
work.
drawing.
Well,
It's
I mean,
not so much
it's
tricks as
both,
the
image
idea of
quality-
subpixels.
Oh,
It's a
image
separate
quality
issue.
was a priority for him.
Right.
Right?
Was
So-
he reading books? We don't know. I think we don't know.
Yeah, I mean, it's not. I mean,
I'll have to send
the
follow-up question.
he was talking to Mike in email occasionally, because. But anyway, so.
I mean, just in my head, just because I guess I'm not maybe explaining this well. At some point, he must have thought about subpixel precision.
I don't think he didn't know it was called subpixel.
I guess what I'm saying is,
it's not-
how did he end up getting a thing like that then? You think he just kind of was like, oh, that looks
I'm
wrong,
sure if we
so
went
I
back
did-
to the Doom code, it's not actually sub. I mean, I don't know for
Okay.
sure, but I'm sure
Sean
that
was
it's got
suggesting
rounding.
it is, though.
No, I mean, it was way more
looked like
subpixel
it,
than
like-
not.
Oh, it looks like it.
if you just truncate to the nearest integers, like
Yes.
shit crawls all over the place, and it
Okay.
wasn't doing that because he filtered every line before he drew it, meaning he pre-stretched it and then did the thing. So if you do that
Okay.
right, and you know,
So maybe he just kind of iterated
Yeah,
and got to a
I-
close
yeah,
thing.
right.
Okay.
Yeah.
All right. So it could be that he wouldn't really have known the like abstraction that would allow you to then apply the same thought process.
Yeah, who
to a
knows? I mean,
triangle. Or maybe
yeah,
he did, but we
I don't
don't
know. We don't
Okay.
know. I mean, because
So-
he also had Wolf before that.
Yes.
Wolfenstein was a similar, I mean, it was only, like the thing about the break from Doom to Wolfenstein was the ability to have things that weren't just box.
Right,
you know,
yes, you could
which
have
required a little bit more
triangle
math
walls,
to set up the columns and the
But
rows
it was
and
also
stuff.
having texture maps on the floor.
On the floors, yeah, because the floors was, hey, the line of constant Z is
Yes,
moving in the
yes,
texture map,
Yeah.
right, as
More than
opposed
one
to,
level floor. too.
yeah.
So
Yeah, but anyway, so
Yeah.
it's hard to overemphasize how much mental power and conversational power graphics took up then. It was just what you talked about if you were a game programmer.
Right.
Like no one cared. I mean, I'm sure some people did, but there was no game design.
Right.
Like as a thing that you could
Right,
talk
right.
about, like, or there was just like, how fast can you get your texture mapper?
okay.
Right?
Gotcha.
And so it was just like what people, all the hardest core, highest end, all the like, everything was just talked about. Just like everyone licensed Smile Sound System or whatever it was called, ALE, and then like spent all their time on their texture mapper. And then so, but so in image quality was the thing, because we had all the like, I mean, the computers were getting faster, and so we had the cycles, and so it was like image quality. So it's like fixing your cracks and getting some pixel accurate and like all these things. And so I just wrote these articles. I wanted to figure out myself.
Yes.
And like Sean was saying, the best way to figure things out is to actually try and write an article about it as an expert, because then you actually have to
So
like.
basically what you're saying is assume you're an expert temporarily, write the article, and then at the end you are closer to being an expert.
Well, or start to be like, I really want to be able to write an article about this
Gotcha.
from the point of view of an expert, so I had better get there, and there's a deadline on the article
Well,
in like 3 weeks.
you'll attract attention from the actual experts.
Right, who will then
who will
correct you.
flame you. And that,
Yeah.
you get to where you're going.
Yeah,
either
exactly.
way.
So, okay, so when you're doing this though, you're looking at this and going, okay, so people are saying that they've got these sort of cracks and dropouts and stuff.
Well, the fill convention stuff was handled earlier, but I just wanted to document it really well.
Okay, so who,
I mean, that's all just been like, I mean, it's just, like, Foley and Van Dam, I think, talk about fill conventions, I think. I can't remember. That's been
So
years.
that was more of a-
Resinham is about fill conventions, things like that, just like what's in and what's out if you're
so
drawing
that was
a
more of a, like a, for lack of a better term, that was more archaeology. It was just like, okay,
Well,
let's
no,
grab the right
because
stuff.
you
and
have to know, if you're gonna, once you're mapping something onto a surface, you have to know where the actual, you have to step to the pixel center from the edge of the thing. So you have to
Yes.
get your fill convention right with the floors and the ceilings, so that if it's right, if the line's right on a pixel center, then what do you do? And just, there's just a whole bunch of little math there that is not a lot of code once you know the math. It just all drops out into like, I add 1 in the low significant bit on this thing and it
Right.
works. But figuring that, a lot of people would just literally have, and I was talking to somebody a couple days ago, I think, that was like, we were talking about, so Under Killing Moon was another game that had a crazy advanced texture mapper
Yes.
that was really garbagey and really crawly, but like it was full general, and it was like 10 frames a second maybe.
Yes, yes.
Because they were doing lots of polygons and lots of
they
textures.
weren't an action game, so they didn't have.
Right.
that
So it's like,
fact.
but Jeff was just saying that.
Jeff Roberts
Yeah,
from
and
Games. He was
Bruce. So
Mr.
Bruce, not Bruce Artwick, but Bruce Dawson.
Bruce Dawson.
No, it wasn't Bruce Dawson.
No,
It was the
sorry,
other Bruce.
Bruce
Johnson.
Johnson.
Yes. That he just had like a magic number he added. Right. I
really?
mean, literally, he just had like a 1 in the 16, in the fixed point, like, and like he just, I don't know why this fixes it. And like, so when I wanted my articles, like, and what it was doing, it was converting a floor to a seal or whatever. Like you add 1 and then truncate, and then boom, it was a seal, and now it's a
So
floor.
you just tried a +1 and was like, hey.
Yeah. Whereas this guy, I think his name was Kurt, but Concrete Mathematics talks about like Concrete Mathematics isn't like the artwork book where it doesn't talk about like fixed point and whatever, but like, if you realize what's going on, you can see all these floors and seals, and you just write out the math, and then you grind it through in the right way, and then it's like, oh, you should add 1 here, or you should subtract 1 there, and then you should, truncate or whatever. So I just wanted to document all that stuff, because there's all this stuff in lots of different places. And as we went towards image quality, it seemed like to me, coming from a basis of, I just reread the intro to my article just on stage here while you're doing the thing, and it was like, if there's one thing 3D video games have to have now, it's a perspective texture mapper.
It's true today as well.
It's exactly true. Words to live by.
So, sorry to just, I know this sounds like I'm trying to pin down something specific here, but I just still am not quite sure. So,
I'm dodging around the fact that I don't remember any of this, so
Okay,
like
that's
I'm
fair.
trying to like
That's
bob and
totally
weave.
fair.
Yeah.
I just wanted to see, though, if I can get it, which is, again, people are having problems with these, like, in other words, games in general are not necessarily doing the right things for their fill convention. So at some point, somebody, and maybe it's, was other people or something, but had to go, wait a minute, there's this information in these other places that's about how to fix that. So I was just asking, what happened there? Was that talking to people at Microsoft?
I mean, I think it's just like
researched that, or-
Usenet, and like everybody
People-
talked about this all the time.
So some people kind
Like,
of figured
yeah.
out, hey, in Foley and Van Dam, there's some stuff about this.
Right, but the thing about so the fill conventions of how to fill triangles was well understood. I mean, Mike had written about it years before, like
Okay.
not. I mean, Mike didn't. I mean, it's like that's just in early graphics textbooks. All had
So
that
it
stuff.
was kind of just been found, just people
Yeah,
didn't
yeah.
necessarily do it. It's just like,
Right. Well, yeah. I mean,
okay, you didn't necessarily read that book or whatever.
right. And then when you add texture mapping, all that stuff gets worse because you have to be on pixel centers. So
Okay.
it all of a sudden you could have had a crappy like solid polygon filler or even a grow shaded one and not notice that you were off. But once you've got texture mapping on there's just this high frequency, you're an idiot like thing on the screen, right?
I think
So-
there is actually a subtler thing, which is the floor mappers scan converted horizontally, and the wall mappers scan converted vertically.
Okay.
And those rules were actually hard to make consistent.
Right.
Like that was a subtlety that no one talked about
Yeah.
because it was a unique thing we were trying to do.
Right.
And probably there's an easy math solution to
Yeah,
it.
yeah.
But nobody had any idea.
Right.
Well, also in general, outside the walls and geometry, people generally used T-junctions without even caring.
Yeah.
Every
Yes.
3 model. I didn't even know the word T-junction.
Right. Yeah.
Like,
Or,
oh yeah, it touches that.
Or bow ties is a similar.
Yeah,
kind of thing.
and also
like, yeah.
we rendered concave polygons because we couldn't afford to break those things up
Right.
too, and it's really hard to get the. So
Yeah.
I just remember we just padded everything by about a half a pixel all the time and hoped it touched.
Yep.
So, and then talk a little bit about just the final state of the articles there. So,
Well, so-
the perspective correct part of that, I guess, was kind of something that came about partially as...
Well, it's just what was happening then. Like people were
Okay.
trying to figure it out or figuring it out. And so Mike had written the affine ones, but you couldn't make a game out of them very successfully because things would just warp massively.
everywhere,
But it was
yes.
cool. I mean, he had his little he had polygons, 3D stuff going on
Yeah.
the screen, and so we were friends and worked together then. And so, and Doom. It was just clear that perspective had to happen for it to be general enough to use.
Yes.
And so, so just documenting that and figuring it out, and we worked on the assembly code and tried to
Documenting what? The
the
like,
math behind it, and then how to write the assembly code to make it work.
And how was getting the math behind it a question of, because again, Sean had written the articles, which you saw about...
So those were all plane equation based. Like there were
Right.
no UV coordinates in his articles at all.
So-
So like the way you actually do a pipeline with this stuff, it was more intuitive nowadays, and maybe it's 6 one half a dozen the other because I know more math. But back then, for me, like the idea of like you've got some source bitmap and you've got a triangle, and the triangle has got coordinates in the source bitmap that you then want to put on the screen made a lot more sense. So I wanted to figure out from there. That's actually the way the hardware ended up working.
Okay.
I mean that's the way the SGI hardware worked before this too.
Yes.
Like that's so I wanted to derive the math from there. But if you look at the articles, there's a ton of plane equations and stuff
did
like
you-
that. Just if you have to be able to detect them.
And you just worked through that math yourself? Or was
Yeah,
that-
yeah.
Okay.
And then if I
that's the
got
part
stuck,
was
I would like ask
the
the guy
other-
whose name I think it was Kurt. But most of the
Somebody whose name we think is Kurt is
well,
the
I
person.
think I think his name is not Kurt because I'm not sure. what the
Okay,
guy's
somebody
name is.
whose name
Yes.
we think is
It's
something
not-
other
yeah,
than Kurt.
Yeah. So, that stuff came mostly. That stuff was more eye-opening for the fill conventions, for the subpixel like gradient stepping stuff. That was basically like if you're off by like 1 bit, like you're gonna find little bugs. Whereas
Yes.
if you can get it exactly right in fixed point to match the correct math.
I see.
If you just do all this stuff, that was really eye-opening to me because that's stuff that I still use now. Like it's
Really?
Still,
So
well,
all
so that's just real math, and so
Right,
you're
right.
like math carries across. I haven't written a non-SSE kind of assembly language in a million. Why would you ever
Right.
write that, right? Because
Right.
you just don't need to do that anymore.
Right.
But that math is useful everywhere. Now that you know that, like a floor and a seal, like seem impenetrable. Like you can't
Yeah.
get anything out of here because it's changing the number, but you can. Like you just have to know.
What book is this again? It's a
Concrete Mathematics by.
It's a Knuth book.
It's
with,
Graham is the first author, and Knuth and Patashnik.
Got it.
Such a great book.
Well, we have to break for lunch. I think we probably got to the end of it just
I think
about.
Basically, yes.
So
Please don't make us talk about it.
Thank you, everyone, for sharing that with us. I'm sorry for taxing your memory.